Hello and welcome to week 4, lecture 3. Today we're going to talk about collisions, impulse, and momentum. This is covering chapter 6-1, 6-2, and 6-3. We will introduce collisions, linear momentum, and impulse, and then we will do 2 examples. So, collisions are a situation when two objects exert a force on each other over a time interval. And the motion that occurs can be separated into before, after, and during the collision. So before the collision, we have these two balls that are moving toward each other, and then during the collision is when they are exerting forces on each other, equal and opposite, and they're in contact over a time interval. And then we have the after the collision where their motion changes due to the collision. We use linear momentum to describe the motion in a collision. Momentum is given by a lowercase p, and it is mass times the velocity. Momentum, as you can see, is also a vector, and it is a vector that points in the same direction as the velocity. And we can see here that this relationship between the net force and the change in momentum over time. So this actually comes from Newton's second law, but we can see where that comes from. So if we say this is true, and then we can plug in mass and velocity for the momentum. And then mass we assume to be constant throughout the collision. So we can pull that out. And then we just have the change in velocity over time, which is the acceleration. So this equation here, which seems like unusual or weird, is actually just Newton's second law in a different form. So the force that acts between two objects during a collision is called the impulsive force. And now we can do the thing that physicists do that mathematicians don't like, and treat this derivative like a regular fraction and multiply dt on both sides. So we end up with dp equals the sum of forces times dt. And now we can just integrate both sides over the time of the collision. And for the momentum, that is going from the initial momentum to the final momentum. And for force with respect to time, it's going from the initial time to the final time. And then this integral of force with respect to time of a collision is what we call impulse. It's given by capital J. And impulse of the net force, which is what this is the change in momentum of the object during the collision. Because if we think back actually on this slide, this side of the equation is just the change in momentum of the object. And this side is the impulse. So they're equal. So we have these two relationships for impulse, that it is the integral of the force with respect to time. And that's the change in momentum of the object during, before and after the collision. Here we have a graph of force over time showing the force between the two objects during the collision in red. So this guy. And you can see that the force is not uniform during the collision. It has a not that gradual increase to the peak, but then a more gradual decrease to 0 over the time. And impulse is the integral of the force with respect to time, which also means this area under the force curve. This is also equivalent to the average force over the time interval. So impulse is also the average force over the time interval. and so is the momentum. And so this black rectangle is the average force over this time interval. Because unless we are actually integrating, we can't get the area for a shape like this very easily. But if it is equivalent to take the average force applied during that time interval, then we can do that. So now we're going to do sample problem 6-1. A baseball, which has an official weight of about 5 ounces or a mass of 0.14 kilograms, is moving horizontally at a speed of 93 miles per hour, about 42 meters per second, when it is struck by a bat. It leaves the bat in a direction at an angle of 35 degrees above its incident path and with a speed of 50 meters per second. So we want to find the impulse of the force exerted on the ball. And if we assume that the collision takes 1.5 milliseconds, we want to find the average force and then the change in momentum of the bat. Okay, so I've drawn the situation for you. This is before the collision, before, and this is after. And so you can see that we have set that the initial velocity of the bat, or of the ball, I'm sorry, is to the left. And then the final velocity is to the right, but at an angle. So we're going to draw those momentum vectors, especially because this part of the problem where it says the ball leaves the bat in a direction at an angle of 35 degrees above its incident path, that is not entirely clear what that means, but I will show you. So because we're saying that the ball is moving to the left initially, its initial momentum points to the left, just horizontally. So this is the initial momentum, and it's just for the ball. And then, so this is the incident path, is the x-axis. And so the ball leaves the bat at 35 degrees above the incident path. And we also know that it must be pointing to the right. So that means the positive X and Y quadrant. So there is the final momentum of the ball, and this is 35 degrees. So now that we have like a clearer visual of the situation, let's also write down our notes. Well, I just wrote down what the angle was, but we're still going to write it again. And then we have the mass of the ball is 0.14 kilograms. And then we have, they told us the initial and final velocities. So initial velocity is 42 meters per second in the negative x direction. And final velocity is 50 meters per second in the positive x direction, but also at the angle theta. Okay, so first they want to know what the impulse is. Change colors. Impulse is the change in momentum, which is the final momentum minus the initial momentum. So let's find out what those are. The initial momentum, just mass times velocity. Mass is 0.14 kilograms and velocity is 42 meters per second. So a note with this one is you could plug in negative 42 there if you want. I'm going to write that it's in the negative x direction, like to keep track. But if you want to plug in the negative sign there, feel free. So anyway, this is 5.88 kilogram meters per second squared in the negative x direction. And kilogram meters per second squared, that's just the units of momentum. They're not nice units. It doesn't get its own like simplified units. That's what we get for it. And then the final momentum, again, mass times velocity, the final velocity. And that's 0.14 kilograms times 50 meters per second. and that is 7 kilogram meters per second at theta from the positive x. So we have an x component for the initial momentum and then a mixed x and y components for the final momentum. So let's break the final momentum up into x and y components so we can better do this math. So, oops, clicking too many things. So we know the final momentum, it's like this. And then the x and y components. So the x component is here. So that's going to be p final x. And that is adjacent to the angle. So that is p final cosine theta. And then the y component, and I just want to show that I am matching these, well, trying to match them to the vector I drew. So this is the y component. I'm going to write what that is just down here because there's not room. PFY equals, and this one's the opposite, so it's sine theta. Okay, so, and we have what the final momentum is. And so now we have the x and y components. And we can multiply them by the final momentum. So I guess let's do that. Maybe we'll just do it right here. 7 kilogram meters per second, cosine of 35 degrees. That is 5.7 kilogram meters per second in the positive x direction for the x component. And then 7 kilogram meters per second times sine of 35 degrees is, excuse me, 4 kilogram meters per second in the positive y direction. So now I'm going to write these vectors in unit vector format just because it makes, for me personally, doing the vector math easier. But there's lots of ways to solve vectors. So it's okay if you are more comfortable thinking about it in a different way. Just make sure you show your work. So the x component, 5.7 kilogram meters per second, I hat plus 4 kilogram meters per second, j hat, and then the initial momentum is negative 5.88 kilogram meters per second, I hat. And now we're doing the momentum, or sorry, the impulse is the change in momentum, which is these subtracted from each other. So that ends up having us add the x components. So that gives us 11.6 kilogram meters per second, I hat. And then this one is 0, j hat. So it's just 4 kilogram meters per second, j hat. And then we can, this is also equal to the impulse. And then we can find what the impulse is itself instead of in component form, the magnitude of it. So that is just the square root of those numbers squared. So 11.6, I'm going to skip out on putting the units in here right now because I'm running out of room. 4 squared. And this is 12.3 kilogram meters per second. And then we want to do the and get the angle, but let's look really quickly what this would look like. This is the initial momentum, and so this is p final minus p initial means p final plus negative p initial. That's what this is, negative p initial. And so we put the tail of p initial on the tip of p final, and then we draw our other vector, and this is the impulse. And we draw it from the tail of the first vector to the tip of the second vector. So here is the angle, and that tells us that this will be the x component, and this will be the y component, or also you can think of it along the y-axis there. And so I'm doing this because we are solving for the angle using tangent, and I need to know which needs to go on the top and bottom so that I can better describe my angle. So that tells me that the x component is the adjacent. So tangent inverse, or we'll call this angle phi actually. Phi equals tangent inverse of opposite, so the y, which is 4 kilogram meters per second, divided by the adjacent, which is the x, so 11.6 kilogram meters per second. And this gives us an angle of 19 degrees. So the impulse is 12.3 kilogram meters per second at 19 degrees from the positive x axis. Cool, but that's only one part. So now it asked us what the average force is, and then what the change in momentum of the bat is. So I'm gonna go to the next page. The average force. So B, average force if the time interval is 15 milliseconds. Is it 15 or 1.5 milliseconds? 1 second. 1.5 milliseconds. 0.0015 seconds. And we know that the impulse is 12.3 kilogram meters per second. So we just learned impulse is the average force times the time interval. And if we want to find the average force and we have this and this, we just divide both sides by the time interval. Get that the average force is equal to the impulse divided by the time. So 12.3 kilogram meters per second divided by 0.0015 seconds. And this gives us 8,200 newtons for the average force applied in the collision. And then C asks for the change in momentum of the bat. So the thing to note is that the force on the bat is just negative the force on the ball. And so that also tells us that the change in momentum of the bat is just negative the change in momentum of the ball. So that means we don't actually have to calculate anything. We just have to add a negative sign. So change in momentum of the bat is negative 12.3 kilogram meters per second at negative 19 degrees from the negative x-axis. Okay, I'm going to quickly walk through that, and then we have one more example. Okay, so we had a baseball hitting a bat. Initially, the ball comes in horizontally, and then it bounces off at an angle from the horizontal. So we were supposed to find the impulse first, which is just the change in momentum. The final momentum had an x and y component, so we had to take that into account. But then we did some vector math and found the impulse to be 12.3 kilogram meters per second. And I also showed the vector math here, so that we had a better picture of what angle we were calculating, and also which should be the opposite and which should be the adjacent side of that. So that gave us 19 degrees above the positive x-axis. Then we also were asked for the average force, which impulse is the average force over the time interval, so we just solved that. And then it asked for the change in momentum of the bat, but because the force acting is equal and opposite, and the time interval is the same, and it really comes from this equation here. So the impulse experienced by the bat is equal to the negative of the impulse experienced by the ball. And impulse equals the change in momentum. So that is how we get that. We just add a negative sign. Okay, now this example. A cart of mass 0.24 kilograms moves on a linear track without friction with an initial velocity of 0.17 meters per second. It collides with another cart of mass 0.68 kilograms that is initially at rest. The first cart carries a force probe that registers the magnitude of the force exerted by one cart on the other during the collision. The output of the force probe is shown here in this graph, and we want to know the final velocity of each cart. So I'm just going to write down what we know. Mass of cart 1 is 0.24 kilograms. Mass of cart 2 is 0.68 kilograms. Initial velocity of 1 is 0.17 meters per second. And initial velocity of 2 is 0 meters per second. Cool. Now I'm going to just quickly draw the carts. So initial situation, we have V1 initial, this is cart 1. And cart 2, just sitting here, V2 initial equals 0. And then after the collision, they are going to be moving in opposite directions. The final 1. This is 1 still, and then this is 2. And V final 2. Okay. Now I also just want to draw us free body diagrams of the actual collision. So when they collide with each other. 2, 1. So for cart 1, it has the weight of cart 1, normal force it's experiencing, and then it is experiencing a force from 2 on 1, or on 1 from 2. 1, 2 then. And so that is pointing to the left. And then for the second cart, same an amount and type of forces, weight, normal force, but then it experiences the force from 2, or from 1, this is 2, in the opposite direction. So force on 2 from 1. The forces. Everybody's a vector. Okay. And then we also have our graph here of force with respect to time in milliseconds, so got to be careful there. And we know that the impulse is the average force times the time interval. And it's also the area under a force versus time curve. So for a triangle, the area is just 1/2 the width times the height. So the height is this maximum value of force, which is 10 newtons. And then the time interval is from 3 milliseconds to 14 milliseconds, which is 11 milliseconds. And I'm just going to put that as 11 times 10 to the negative 3 seconds, because milli is 10 to the negative 3. And this is 0.055 kilogram meters per second, or Newton seconds. Those are the same units. So let's see. we also know that impulse equals the change in momentum. And for cart 1, the force acts in the negative x direction, so that's going to be the negative of the impulse, negative j. And the for the cart 2, positive j. So let's look at cart 1. So the change in momentum of cart 1 is just the final momentum minus the initial momentum. 1. And let's rearrange this to solve for the final momentum. So we'll just add the initial momentum to both sides. So that gives us the final equals the change in momentum, or the impulse, plus the initial. And then for this, we'll plug in the equation for this momentum, because we're solving for the velocity, not the momentum itself. I mean, I like to do it all at once. So mass 1, final velocity, change in momentum plus initial momentum. Then we just divide mass 1 on both sides, and we get the change in momentum plus the initial momentum over the mass. And so now we plug this in, and remember that the change in momentum for 1 is negative the impulse, so negative 0.055 kilogram meters per second, plus the mass of the first one is 0.24 kilograms. And the initial velocity is 0.17 meters per second. The whole thing divided by 0.24 kilograms. So this is negative 0.06 meters per second. So that's the final velocity for mass 1, our cart 1, same thing. Let's do for cart 2 now. So this part, and again, for cart 2, this is the positive of the impulse. So it is the final minus the initial, but it's initially at rest, so this is 0. So the final momentum is just equal to the change in momentum, or actually the impulse. So we need to solve for velocity though. So we plug that in. I'm going to list this as the impulse, and we just divide the mass on both sides. So we get the impulse divided by the mass, and the impulse is 0.055 kilogram meters per second divided by the mass. Is different for this one, 0.68 kilograms. And we get a final velocity for this of 0.08 meters per second. So that is the final velocity of the second cart. Okay, I think that's everything it asked for. Yes. Okay, so briefly just go back over it. Had 2 carts, one was moving toward the other one wasn't moving. And then they collide, and we want to know what their final velocities are. And we drew free body diagrams for during the collision, so that we had a better perspective on the directions of the forces they're experiencing. And then we found the impulse, which is just the area under the force versus time curve. So for a triangle, that's 1/2 the base times the height. And so we got 0.055 kilogram meters per second. And from looking at our free body diagrams, we saw that the force for cart 1 is in the negative x direction. So that means its impulse is negative, the impulse. And for the second cart, it's just going to be opposite. So that one's positive. And so then we know that the change in momentum is equal to the impulse. So we just solve for that, rearrange some stuff, made sure we were careful about the sign, and we got the final velocity for cart 1 to be negative 0.06 meters per second. And then for cart 2, the impulse is positive and the initial momentum is 0 because there was no initial velocity. So then we get our final velocity for cart 2 is 0.08 meters per second. Okay, so that is your introduction to momentum. I hope you have a great week.